all set to welcome Gaurav, who's got a background in actually doing a lot of this stuff in practice, especially around ADAS, sort of autonomous driving sort of stuff. And I'm really excited to see what you dive into. So take it away, Gaurav.
Okay. Hello, everyone. Good evening. So as I was introduced, in working in perception and system side for most of my career, and recently, we are working a lot on the data side. And in today's talk, I want to talk about how to ensure quality data for your deep learning, and focus on sort of collection, curation, and the annotation piece. So that's sort of the outline of my talk. We're going to initially talk about the motivation, like why data is important. What's sort of the main part that we need from data in sort of the whole deep learning journey. Since when we started working on CV initially, we didn't need such huge data sets. We had sort of more handcrafted features. So how do we look at data now in the deep learning world? That's what we'll start with. And then we'll talk about sort of the collection, the curation piece. And by curation, I mean making sure the data is something which is useful for our particular application and is also improving our application sort of going forward. For the annotation piece, it's often neglected. And I want to talk about that as well and talk about how to create instructions for annotation and so on. And then we'll conclude it all. So just before I start into the meat of the talk, like how many out here are data engineers? Okay, see 1, 2, 3, okay, 4 of them, that's good. How many are data scientists? Okay, a couple of them. And how many are ML engineers or work on deep learning directly? Okay, a few more there. Okay, good to know about the crowd. So what often we see is, we have a lot of people working on the ML side, on the ML engineering side, sort of creating new models, working on the models. But if you have garbage data coming in, your results are not going to be good, right? So the data engineering part is often, when you start a project, you think about, hey, let me get some ML engineers who've written papers in CVPR or have some excellent experience. But a lot of times people miss out on the data engineering aspect, right? So that's where it's very important to have a good mix in your team and a good mix of people who also understand the data side of things. So today I'll talk about the collection side. You can buy some data from time to time. You can use some open source data sets. You can collect your own data, right? And once you're in production, you can get some more data to sort of improve your current performance. And then in the curation, I'll talk a lot about active learning. It's a technique that I really must hammer down you guys must use if you're setting up any vision deep learning method. It's really going to help you in getting the right data for your application and improving your performance. And the last part is the annotation, talking about auditing, talking about doing it in-house and managed. And I've done both of these. So I've used a managed service before. I've also set up an annotation team myself. So I can talk about sort of real-world examples of what was good, what was bad in all of these things. So we'll talk a lot about pros and cons in different options you might have for all of these things. We'll talk about challenges, and we'll talk about some interesting experiences that I've had. Okay, so starting with data collection. You have like 4 different kinds of data sets that you can think of, right? So one is sort of your open and free data sets. They're typically licensed under something like Creative Commons Attribution 4.0. It's fully open. You can use that data set for any commercial application. But often those data sets, you can see kinetics in there, for example, is used a lot for research. So you'll have this data set sort of created for A research activity, kinetics, for example, is on the action recognition side. So what is a person in this video sort of doing? Is he sort of picking up an object? Is he sort of playing drums? Those kind of things. A lot of times these data sets are not very useful for end applications or like production level applications. They're useful for research. So that's one major con of this data set. But on the other hand, there's a lot of research interest in these data sets. So what you'll find is a lot of publications focusing on them. You'll find maybe some code also for training on these data sets. You'll find things like data loaders, which are important for ML applications already ready. You'll have a lot of comparisons between different methods on these data sets. So they're really useful when you start out in your initial journey of building sort of your own ML CV system to look at which algorithm you might want to use, and also getting an initial prototype out, maybe just an internal demo or something that you might want to use. And also in the past talk and talk just before, we talked about fine-tuning. If these data sets are open, you can use them to sort of train your initial network and then fine-tune on some more specific data set as well. And that could be your own data set or some commercial data set as well. So this is the first sort of type of data. And the second type would be a licensed paid data. So this is companies like Mapillary, for example, who've understood that there is a space for some data to be used by different companies. They've collected a lot of data or crowdsourced it and then annotated it to a good level. And that is something that they're selling in the market. You'll see some research interest in these, because many times what these companies will do is they'll open this data set for download by universities, but will disallow that from companies. So you can't use this data set in your commercial applications, but you can use it for research. And typically you'll see universities sort of using this data to, again, create some models, give some comparisons, present some papers. So that's the second kind of data set. It's sold and can be something that's going to be high cost to you. And one aspect there is if your application is very specific, this might not meet your needs, because they do the annotation for sort of a more general case for multiple companies that might be interested in it. And if your application is kind of niche, the kind of labels that you want might not be in this data set. Coming to the third type, which is your own data sets. And we'll focus on this in our talk, how to create your own data sets. So once you've done with sort of looking at open free data sets, doing some prototype, maybe you looked at some commercial ones that are available, licensed ones that are available, and they maybe cover some of your use cases. Then you say, hey, I want to push my application to the new level, to the next level. What do I do there? When you start collecting your own data, there are certain pros there. You can really filter it for your use case. You have full flexibility in your labeling. You can decide, hey, I want to label, road signs in this particular format. I want information about is a stop sign occluded or not. I can add any attributes that I want to the labeling as well. So I have a lot of options when I do sort of labeling on my own versus when I pick up any open data set or licensed data set. Now, this metadata is often important. For example, like occlusion can be used as a very important indicator of the difficulty of that data. So if I find an image where there are a lot of occluded signs, I might want to focus on them in my training. So this is something I can do a lot with your own data sets, and that's a big pro. But a con for the own data set is that it's very costly to collect, and it's very costly to annotate as well, both in terms of time and in terms of resources. And we'll talk about that in more detail when we get to this annotation piece. The last type is very interesting and has seen a lot of interest in recent years, synthetic data sets. And from the world that I come from, ADAS and AV, we're looking at a couple of companies that are mentioned over there that provide this. We are able to sort of reach 98, 99% of performance with real-world data, but we're not able to pick out specific corner cases in our data. Especially if you're a smaller company, you might have issues in sending like huge fleets out there to collect corner cases. This might not be true if you're like a big company like Waymo or Tesla. You might have a lot of vehicles, a huge fleet. In case of Tesla, like an OEM fleet collecting data for you. So you might not need synthetic data as much, but I've actually seen even Tesla or Waymo use synthetic data. The reason for that is even for perception, it's something that's useful, but scenarios, for example, accidents, they're very difficult to get, even on production fleets. So you have to sort of collect data for years before you start getting all kinds of accidents that are possible. So specific scenarios can also be created in synthetic data. And synthetic data companies are sort of doing well in creating data for a lot of perception use cases, ADAS and AV, but also in other use cases. Now, the main issue with the synthetic data sets is the reality simulation gap. So if you train simply on simulation data, is that going to be good enough or not? That's something that you have to think about. So when you do your own data set collection, what do you need to do? You need to start off with what sensors you want to use. So typically, there would be cameras, there would be lidars, for example. There would be some GPS, INS units to give you localization information that you can then use to sort of see where you collected your data. You need to create a sensor rig, right? On the right is an example over there. You have a lidar over there. You have some cameras. Actually, you have 3 lidars over there. Once you have your sensor rig decided or the sensors that you need decided, you need to do a calibration of them. And this is both intrinsic and extrinsic calibration. By intrinsic, I mean like a camera, getting the camera matrix for that. For extrinsic, you're sort of calibrating across different sensors. So you say, what's the transform between data that we collected on the lidar versus the data I collected on the camera? How can I put them two together? So this might be useful for, say, use cases like depth prediction, where I want to do depth prediction on the camera as well, and I want some ground truth from the lidar. Or I want to fuse the data together. I want to do detection on the camera and then detection on the lidar and then fuse the data together. So for this, calibration is extremely important. But one issue with calibration is the need for recalibration. When we go on an actual production system, often what happens is that the sensors shift slightly. There would be some wear and tear, there would be some sort of bump the car might hit, and the sensors will shift slightly. So how do you do sort of recalibration is something that you want to think about. Typically, what we would do is do online recalibration. An example of that is, say you're driving outside, there are lots of edges that are there. So you have the edge of a building, or you have the edge of a traffic pole, things like that. Now, in the camera image and the lidar, both of them will show up as edges. In the lidar as a depth discontinuity, and in the camera as sort of an edge. Now, this is sort of a correspondence that you need to create between these two. If you see these two not lining up, that means that the calibration has gone wrong in some way when you try to superimpose these two. So there are lots of techniques for sort of online recalibration, but you can also bring the vehicle into sort of the service center and then do a recalibration as well. But typically what you would do is on a production system, first you will try to detect and solve small recalibration issues. And if there's a larger one, you would actually recommend the system comes in for a maintenance schedule. The third point over there is also very important, and I've seen huge issues in time sync. When you connect your sensors to sort of your board, you might have sort of multiple processors running, your camera connected to one processor, your lidar connected to another. How do you sort of sync all of these data streams coming together? Do you have a single clock source or not? How are you getting the exact time of trigger for your lidar, the exact time of trigger for your camera data? So some of these sensors might have hardware triggers. So a lot of cameras nowadays have hardware triggers. So that's what I would recommend to use. And then in the lidar case, each sort of scan of the lidar will also have a timestamp associated with it. So you need to go down to that level to get good sync on the time side. And this is very important, especially for fast-moving objects. Otherwise, your syncing is all going to be messed up. You'll say, here, this object's over there, and for the lidar is certainly behind. And it's going to cause delays in your warnings, in your activities that you want to do in terms of avoiding obstacles. So time syncing is something that's very important. And again, it's something that's given less importance by a lot of companies, but it's like a huge beast on its own. Coming to some more challenges, how do you plan where you collect your data? So when you talk about ADAS and AV, typically companies will collect data around their office. They would have maybe some fleet which will be sent out to collect data on specific routes. But what you need to understand is what's sort of the heat map. Where do you have more data, where you have less data? There's a lot of legacy data also involved. So what happens is, typically, the ADAS AV cycle is pretty long. You take a long time to sort of develop these applications. There's a lot of legacy data that's lying around. And you want to collect new data. You want to understand where that old data is already collected, and then sort of plan, okay, maybe in little Tokyo, I don't have too much data. I need to collect data over there. Or in this case, try to think about Bunker Hill, why I don't have more data over there. And also you need to understand, like sometimes the sensor rigs also change. So once the sensor rig changes, the old data is useful to some extent, but you want to make sure that you have at least some data from your new sensor rig in new geographies. Data collection is also very costly. You need to have lots of vehicles doing this. You need to have sort of a good data infrastructure team, which is planning out how you are taking this data when it comes to your office. So I'll give you an example here, the NIFI, Apache NIFI system. What you can do with this, and we set it up after a lot of sort of scripting on our own and all of these things, but we found this system was really useful for us. It's able to get a trigger on when the data comes in. So when you connect your, through a PCIe bus or a USB bus, you connect your data, you're able to get that trigger and then immediately start your data copying process, and you can copy it to multiple places. So say you have an on-premise storage system, and then you have something on a cloud, like an S3 system or an Azure system. You can easily sort of use these tools to have multiple pipelines sending data to different places. And then you can also set up like Slack alerts for, hey, now your data is copied, now you can start the rest of your pipeline. And we'll talk about the rest of the pipeline as well, because once the raw data comes in, you want to do some processing on it. And that's what we talk about here in this slide. So you've collected your raw data, and now you want to understand what kind of data you have. And we talked about sort of the heat map. That's one thing. But then you also want to understand more aspects to that data. So it's maybe not so visible there, but on the right side, I show sort of a heat map on the ego vehicle. So what kind of state the ego vehicle is in. Is it cruising? Is it accelerating? Is it decelerating? And then traffic map or traffic infrastructure elements. So example, is it accelerating at a junction? Do I have data for that? Do I have data for, it's cruising in a clear area? How much, I have a lot of data for that, for example. Hey, I don't have too much data for, accelerating in a parking space, for example. I see there's no data over there. Or, I have less data for cruising in a lane. So I need to collect more data for that particular use case. So collecting metadata when you do collection is very important. It gives you where, what, and when things are happening when you're doing data collection. And it'll help you understand gaps in your data collection and target all the underrepresented scenarios. So a couple of examples here in terms of like snowy days. You might not have too much data for that. So you might want to target your data collection campaigns around those scenarios. Or look at synthetic data. So when you go into production, there are some things that you can do to make sure the data from production is coming back to you and you're improving your models. And this is a great example here for an occluded stop sign or a stop sign that's a bit far away. You see, when you come closer to it, you're able to detect it just fine. But when you were further away, it was not really showing up. Now, why was that happening? Is it occluded? Is it that my network is not doing well for that kind of stop sign? Maybe it's placed in a different area. Maybe it's placed to the bottom side. That's an interesting data to send back. So when you have a production system, you can look at confidence scores, the ML confidence scores. You can look at ambiguity in the data. So it was detected when you were close. You can send the earlier frames for annotation. So this can be good sort of data collection on a production system that we want to look at. Also, you can use customer feedback. So in the ADAS and AV world, often what happens is you might give a warning to the driver, but if he doesn't brake and he actually keeps going, that means your warning was a false positive. And you want to send that data back, right? Or in the AV world, you have a customer actually take over while the car was driving autonomously. That means that at that point, there was something interesting that happened. Maybe your system was not safe, and the customer didn't feel comfortable and wanted to take it over. So you want to take that data back and try to analyze it, try to run it in simulation, try to see what you can do better in that situation. So we talked about production systems, but what about corner cases? So here are a few examples. There's a small lane over here, and you want sort of a speed limit sign for 5 miles per hour. You rarely see that in real-world data. And you also see the lane is kind of flooded over there. You have some water inside. These kind of corner cases are something that you want from synthetic data. It's something to take your performance from, say, a 95, 98%, all the way to the 99%. And what we see in synthetic data are sort of two major ways in which we do this. One is very intensive talking to your team. So you will come up and say, hey, this is the scenario that I want to be created. And you'll talk to the simulation company, and they'll create those kind of scenarios for you. The other way simulation companies are working now is they're providing you the whole tool, and you can just input things, and you can procedurally generate data. And it can be single frames, or it could also be scenarios. So for example, I talked about accident scenarios a while back. That could be an example of a scenario that you want from synthetic data. So synthetic data works really well when you mix it with real-world data. You don't want to be training your system only on synthetic data in most cases, certainly in the ADAS and AV world. One other important aspect in synthetic data is you want to mimic your camera parameters. And that's a very tricky thing to get done. Again, the synthetic data companies work very closely with you to sort of understand your camera parameters. You give them the sensor type, you give them a lot of sample images, videos, and they look at that and try to mimic your camera performance as much as they can. So it's a very close integration right now in most cases, but they're sort of moving more towards generating these scenarios procedurally. And that'll make synthetic data more useful going forward. Okay, so we talked about the collection aspect. Yeah.
Is it recommended to use GANs to generate the synthetic data?
To use GANs, you say? So when you use GANs, you're sort of having artifacts in those GANs, which is something that you might start learning. So it depends on your application. If you're able to get good quality in your GANs, the output from your GANs, in the whatever you're generating from them, then yes. But typically, what we see is like better performance when you use kind of synthetic data from sort of game engines. So you have Unity or Unreal Engine being used. They're also more accurate on the physics side of things. So you'll be able to create sort of better scenarios from them, so like accident scenarios and things like that. So that's difficult to do with GANs. With GANs, maybe you can do like some kind of domain adaptation. So you can say, hey, how does this image look in winter? You have this image, and you have, say, another image of sort of a wintry scene. So you can do sort of a transformation from one domain to the other. They're really good at that. So I would use it for sort of some transformation in that sense. But if I want really rare scenarios, I would look at synthetic data. Okay? Yeah. So it's useful in some cases, like when you want to do some domain adaptation. So you want to train better on some snow data and so on. But if you want to create some more scenarios, then you want to use synthetic data. Yeah. OK, so we talked about data collection now, and we come to the next important piece, which is the curation aspect. OK, so you have your raw data hitting your servers. You've used something like Niffy to send it to sort of say cloud, and you have something on your on-premise. What you want to do is you want to run some pipelines to get more insight into that data. That could be deep learning networks, and you want to tag the data. So you can see some examples over here. In a particular sequence, you have like a vehicle coming 43 times. You have like a cruise situation. You had some bicycles a few times. You don't want to run networks like at the end of the, after you've sort of trained and you've done everything. You want to run some, dirty networks which might not give you the perfect performance, will give you an idea of what your data contains. Okay, so this is to give you some better metadata tagging. And there are lots of tools out there for this now, and I'll talk about them in the next few slides. What you can do with these tags is then you can actually search the database for where I'm finding these particular events that I'm looking for. Data scientists can then use them and create batches of data for annotation, right? So typically there would be like a GUI or like a Jupyter Hub notebook that people will use, and they would search a database for interesting events that are useful for annotation. And here is a good example. So say I want to search for a stop sign in a construction zone, or I want to search for a stop sign which was with a highway looking in the front. I would use a GUI like this to sort of enter different criteria, and I can add different conditions to it. And then I can see the video, and I can select if this data is something that's useful to me, and then collect a clip and then send it forward for annotation. So typically such tools are used by data scientists, and they would look at a lot of the raw data that's been collected and try to understand which data is important for the annotation piece. And the next slide, I show another example, and this is one of the companies that's here, Voxel 51. So we are looking at certain other aspects as well. Can you do similarity of images? So not just like sort of tags that are written by humans, but can you say, hey, can I find an image like this one? So it might be an interesting image where there was a lot of glare, and instead of like maybe my system is not having this metadata as glare, I can actually use the image features to search for another image. So image similarity is also an interesting way of searching for images that will be important for tagging. Say my model is not doing well on certain kinds of images, I can then look for similar images. I can also compare the ground truth. So if I have annotations already ready, or if I have some initial annotations done by my metadata system, I can look at my production system and then see how well it is doing versus the ground truth. Typically, when we are deploying networks onto the edge, the network is kind of smaller. The performance is not so good. When we are doing things in the cloud, we can actually use larger networks. We can use networks that are more accurate. And we can do a comparison between the more accurate network and the one that we are deploying in production, and then see where we are doing worse, and then send that data for annotation. So that's another use case on the curation side. Okay, so coming to an important piece in data curation, active learning. So we talked about some ways in which data scientists can query the data. They can use some image similarity measures. They can write out some code or some natural language to search for interesting data. How can we automate this process? How can we remove the human out of the loop? The human is still useful because automated techniques have drawbacks. But we want to reduce the human intervention as much as we can. And that's how you do it, using active learning. So active learning, I've given 3 examples here of how you might implement active learning. And in the next slide, I'll talk about one of them in more detail. One example is, once you collect your data, you look at the entropy between the customer model or your model that's going on the vehicle and other high performance models, right? So you might have something that's running on the cloud that I mentioned. That's one way of doing it. The other is sort of uncertainty in your customer model. So typically when we do classification, there is a probability measure that we get for the class that we are predicting. We can use that, but deep learning methods are notorious for being sure about predictions that they're actually very wrong on. So how do we convert that probability of prediction that the deep learning network is giving into a more reliable indicator of certainty is something that I'll talk about in the next slide, right? So that's an interesting area of research. And then we also talked about the sudden appearance of the objects. That's also part of active learning. So with this active learning workflow, what you're thinking about is, I don't want to randomly select data that I want to send back. I want to be very careful in all the data that I've collected. I want to pick out the interesting examples and then send them to annotation, because annotation is expensive. Okay, so we talked about how deep learning confidence scores are not reliable. What can we do then? So there's this very interesting technique called Monte Carlo dropout or MC dropout. We convert our deep learning network into a Bayesian network. So the probabilities that are being spit out by the network actually make more sense. They are probability values. So instead of using a single network, we actually use dropout not at the training time, but at the test time. And with that, we sort of get a confidence value on our prediction, because we can use that ensemble to see how sure we are of our predictions. If all the networks in the ensemble are saying, hey, this is a car, perfect, that's great. We are very confident of this. But now that you use dropout at prediction time, and sometimes the network, some of the ensemble members are saying, hey, this is probably not a car, it's maybe a truck. That's an ambiguous example that you want to use, right? So the MC dropout is a very powerful technique. It's something that we've used a lot to sort of understand which data we should use for annotation. And I would really encourage you guys to check this one out. Okay. So you curated your data, you collected it. Now we come to annotation. Now, what kind of annotation could be there in sort of an ADAS and AV case? And some of these cases are also true in other applications. You might have bounding box annotations, and you might have semantic segmentations. Think of it in terms of an annotator, like a human who has to do these activities, right? For a bounding box, the human annotator needs to know what classes he needs to annotate. And then he has to learn to draw sort of bounding boxes around these classes. Pretty simple, right? Well, think of the fact that many times we have to do this over videos. So we have to actually do tracking as well. So the tooling is very important for us in bounding box, especially for video annotation, to help the annotator sort of do annotations across different frames and then associate bounding boxes across different frames. So when you use a lot of annotation tools, you'll see sort of tooling around how to help people for bounding box, especially on the tracking side. Semantic segmentation is much tougher and is more expensive hence. Why is that? Because you need to get pixel level perfect, right? There are some tools out there in semantic segmentation that can help you. So you'll find some automatic tools that will help you sort of segment the image on a more image processing scale. So you'll sort of create super pixels, and you would just annotate the super pixels. That'll help you sort of get edges that are important and so on. But semantic segmentation is the much tougher job here. This example over here shows semantic segmentation for a road scene. You can see a lot of lanes. You can also see a bike lane, and you can see a sort of drivable space as well. So that's the one in red. There are also 3D annotations. So when you look at lidar images, you have to do 3D annotations using 3D bounding boxes. And that's also pretty challenging. Think of it as you need to look at different views of the same object. You want to make sure that your cuboid is correct. So generally in the tools that are used for 3D annotation, you'll find different views of the same object. So once you create like a cuboid around the object, you can look at the side view, you can look at the top view, you can look at the forward view and try to see that you're correct in all those sides. You want to make sure all the points are lying inside the cuboid. There's also segmentation as well for point clouds, which is also a challenging activity. And on the left, there's also text annotation. That's given as another example. So a lot of the companies that you might work with annotation, they also do this activity as well. So when you send data for annotation, what are sort of the steps the data goes through? And this is a workflow that is used very often, but is very difficult to get right. And I'll explain why. So with the workflow here, you create instructions for annotators. So you work with a company or you have sort of an in-house team, you create some instructions. You talk to your data scientists, they tell you, hey, these are the classes that I want. You create the instructions, you send it to the annotator. Typically, you want to send them some limited amount of data. You don't want to just start off the annotation process straight away, especially if it's a new task. Send them a little amount of data, and then you see what they do, what they annotate with the instructions that you gave to them. Because often, instructions given the first time, they're not very reliable. There are lots of issues in instructions, because for data scientists, a lot of things are obvious, but they're not able to put pen to paper for those things. So you want to make sure you want to look at the annotations that the annotators did, and then take that feedback and create revised instructions. So after a couple of cycles of these, you have sort of good instructions. Your annotation is at steady state, great, that is excellent. But what about QA now? Because you'll have some annotators who maybe didn't do a good job, or there were some issues. So sometimes you would do QA that's automated, but you also want to do a human level QA as well. So typically you'll have data engineers or some of your data scientists look at select batches of data and then try to see, like, say the batch was 1,000 images big. You do a audit on about 50 to 100 images. And generally you'll have a service level agreement with the annotator, or if it's an in-house team, you'll also have an agreement with them that if you're having error rates greater than 5%, then that whole batch would be rejected and needs to be done again. So that's where sort of the rejection of the batches comes in, and then the re-annotation has to be done. Maybe there will be some instruction change as well. Maybe there was something that was missed. So that's something that we want to keep an eye on. Okay, so annotation instructions, real-world examples. Sun glare. Okay, so we wanted to make a classifier for sun glare. for a human, the classifier for sun glare is very sensitive. So on the left image, I don't know if you can make out this, or actually on the bottom image over there, there's a little bit of sun glare, and we found that our annotators were annotating that as sun glare. Now, we didn't want that. We didn't want that small level of sun glare to be there in our data. And that was because initially when we created the instructions, we just gave them a few examples like the ones on top and said, hey, this is sun glare. Now, they took that to whenever there is a little bit of sun in the image or some kind of flaring effect that's there in the image, I'm going to annotate that as sun glare. So you need to give them positive examples and negative examples. That, hey, when you have a little bit of sun glare over there, don't annotate it. And actually give them an example as well to show them that. So typically, annotators are not thinking like data scientists. They're not thinking that this system is going to be trained. There are some small changes will not make too much of an effect. We need to make sure that they get positive and negative examples to get accurate annotations. An example over here. So we told them that, hey, mark the entire lane and gave them an example like that on top. Some of them did not mark the lane to the bottom of the image. Again, it was something that we thought was obvious, but is important to, again, point it out that this is incorrect, sort of not extending it to the bottom of the image. Similarly, a curb detection on the right. The top one is correct, but you can see a little bit of curb, so that's actually a sort of a driveway. So we need to say, hey, make sure driveways are not part of the curbs, right? So any ambiguous situations that you can think of, those need to be called out very clearly for the annotators. And you'll see this when you do that small batch of data, and then you get back some annotations. You can see these kind of issues, and then you can go and update your instructions. Okay, so this is also another example of a different kind of annotation, which is a scenario annotation. So say you want to annotate cut-ins, or you want to annotate, some actors that are turning across in the lane. You need to give some kind of description, give a very clear design over here, visualization that's showing the ego vehicle and the other vehicle, and showing sort of some examples there. So this kind of visualization really helps the annotators sort of understand what you're saying instead of just a description. But the description is also useful for them to understand and sort of compare notes on both sides. Okay, so your annotators have annotated some data. There's still some issues. You corrected your instructions, but there's still some issues. And maybe those issues are not enough for you to reject the batch or re-update your instructions, but just give them a little bit of feedback. So you'll find that in a lot of tools that are out there, you'll have a section for when you reject the image, what kind of feedback you want to give them. So you want to make sure that the feedback is very precise, but also gives them exactly what was wrong. Just don't say, hey, stop line is wrongly marked. You give them that number of the stop line. So in this case, it was stop line number 2. And each annotation typically has some code associated with it or some number. So you would use that. And the example over here, you can see bounding box for this car was wrongly marked. And then other bounding boxes have some minor errors. But the main reason for rejection was the car B771. That one was wrongly marked. Okay, so when we do annotation, I talked about sort of in-house annotation and a managed service. What do I mean by a managed service? Managed service means I just collect my data, curate my data, and then give it to a provider that's going to take care of all the annotation for me. But typically, your input is not restricted just to giving them the data. You also need to do the QA audits as well. So this slide kind of shows the advantages and disadvantages of in-house versus managed service. The quality in in-house can generally be higher because you can train those annotators a lot, and you have full control over their training. In a managed service, again, it depends on the provider. Some of the providers actually use some freelancers, so you'll see Mechanical Turk or something being used, and the quality can be very questionable there. So your QA efforts are more intensive when you have a managed service that is using freelancers. So a good question to ask a managed service is that, do you have your own team? What kind of training do you provide them? Do you have freelancers? Okay, what's the percentage of your freelancers? Do you have like 50% freelancers and 50% your own team, or 100% your own team? It's very important to know. So when we typically started, or we started our annotation process at our company, we are sort of toying with both of these ideas. So these criteria are what we used to sort of decide. We talk to the annotation providers and ask them about the team size. We also check how easily they can scale up, right? So that's one of the advantages in the managed service. Generally, they have a bigger workforce because they are working with lots of companies. So they can scale up much faster than you can do with your own service, because you need to hire them, you need to have management around them, you need to have tooling around them as well. So that's another important thing. You need to develop a tool, or you have to purchase a tool. Now, a few years ago, we didn't have many tools available, but recently there are lots of interesting tools that have come out, and a lot of them have a lot of AI applications as well. So they will do some initial annotation for the annotator, give him sort of an initial guess of where objects are, and then he can do some improvements to that. But it's a double-edged sword. We'll talk about that in the next slide. In a managed service, a lot of these companies have good tooling. Think of companies like Scale. They have excellent tooling for their internal use case. They also have good QA dashboards. So that's generally an advantage for the managed side. In-house annotation, it takes much longer to set up the team. But as we said, when you really want quality annotations, that's what you want to do. You want to set up the in-house annotation team. Okay, so why is quality annotation hard? So we talked about I'll come to the second point first, which is the ML assistance. And why is it a double-edged sword? So if you have initial guesses given to the annotator, he might think, oh, this looks correct. This is absolutely fine. But if you really want like absolutely pixel perfect semantic segmentation, which you do in some critical cases like ADAS and AV, you can't really allow ML assistance to go out of sync. You want to make sure that you have the annotator spend enough time on the image to validate all the ML annotations that were done. So typically what you'll have is on these tools, you'll also have a timer for how long the annotator spent on a particular image. You don't want to spend too long, but you also don't want to spend too less. So that's why ML assistance can be a double-edged sword. You want to make sure that it's helping improve quality and not reduce it. Bad annotation instructions are another huge issue in the industry. That's where sort of doing the small batch and correcting your instructions comes in really useful. QA in a lot of managed services can be very automated. So you'll not find that they spend a lot of time in looking at the images, and they mostly rely on you to do the manual batch processing. So in our case, we had to sort of set aside one person to do, understand the different batches that were there and do a QA audit on them. And this can be sometimes very taxing. So generally, what we typically recommend to do is not have just one person, but sort of rotate that activity around the team. So the QA can be difficult in the case of managed services because it's mostly automated. Then you have a lot of tooling issues. So maybe I talked about a scenario annotation case. It's not something that a lot of managed services provide, or even some of the labeling tools provide. So in the case of scenario annotation, we actually ended up making our own tool. So we had our UI guy and a backend guy sort of work on it for 2 weeks and create a pretty decent tool that could help us for scenario annotation. So depending on your use case, if it's very niche, A lot of companies might not have it supported in their tool, and you'll have to create your own tool. Okay, so in conclusion, what are the key takeaways I want you guys to take from this talk? Invest in tooling, invest in infrastructure, invest in data engineering. It's often, we look at sort of ML engineers, we look at sort of the research side of things a lot, but we don't invest in sort of the tooling around that's really going to help them be effective and create a good production system. Active learning is key, especially during the curation stage, and I'll really recommend you guys to go and look at active learning, sort of understand the MC dropout, understand how to create Bayesian networks, and use them in your use case. We want to make sure that we are continually improving from data coming from production systems. You're improving your accuracy more and more. And you use synthetic data for those hard-to-find corner cases. That's also a key takeaway. And then last but not least, pay attention to those annotation instructions. Make sure you're iterating over them. You're seeing the annotator feedback if they are making some mistakes. Not just their verbal feedback, but the actual batches that are coming back to you. You go and look at those, see the common mistakes that they are making, and then update your instructions accordingly. Okay, thank you.
Thanks so much, Gaurav. That was awesome. So do we have questions? If you want to come up to the microphone so we can catch it on the recording and everyone else in here, that would be great.
Hi. I'm Shota. Do we have a kind of any metrics or indicator which we can know the quality, or we can measure the quality of the data set before actually using it for training? Because the training of AI costs quite a lot in terms of the
as well.
Yeah.
Yes.
So if we can know the quality beforehand, it may help.
Absolutely. So I'll go back to the slide where I talked about the collection. So we need to start from collection itself, right? So there might be mistakes on the collection side as well. So say your sensor was not working. You collect your data and your sensor was not working, or there was some obstruction in the sensor. So you'll find a lot of companies, they're investing in sort of automatic cleaning methods. You might have seen Waymo's lidar, which has a cleaner, it sprays some soap and water, and then it sort of has a wiper as well. So you want to make sure your data collected itself doesn't have any issues like that. So when you have your NIFI pipeline, for example, when you're getting your data in initially, you want to run some basic checks on that data. You want to make sure that the size of the data is expected. So for example, if you collected camera data, your camera data size is to an expected level. Otherwise, there might be some issues in sort of your frame rates. Maybe you're dropping frames. You have some issues with that. So you start with collection. And then later, what's important is your annotation side, right? So when you have the annotation done, you want to make sure the quality of the annotations is checked on a batch level, but then you also have some automatic checks, right? So if you have certain gold standard images that were inserted, right? So what you can do is, like, instead of just doing some batches, you can always set some gold standard images into all the batches and make sure they're repeatedly annotated. So that makes you more sure that, hey, this data is very, very accurate now. You know that these batches are done well because the gold standard images were also done well, right? So those are some ways in which you can sort of maintain the quality of your data set. The other thing is, when you have certain images or certain video samples that are there, you want to make sure that the data that's annotated in all of them is sort of from different areas, yes, but can you also add a lot of synthetic data to it and then see what you can do? Synthetic data annotations, I didn't talk about that in my slides, but they are extremely accurate, right? So what you can make sure is that, hey, can I use some techniques where I can mix synthetic data in with some of my real world data, and how much is the improvement I'm getting from that? Say that your test set is very accurate and your training set has a lot of issues. When you add synthetic data and if you see a huge jump, that means, hey, I need to go back to my training set and try to understand if there are some issues there.
Thank you for this wonderful talk. My question was, do you have any recommendations for how to handle the case where you might have multiple or duplicated labels, for example, from having multiple annotators, or you do a bounding box first, and then next time you do a segmentation, and you can derive a tighter bounding box. Do you have any recommendations for how to handle those cases?
So when you mention sort of the bounding box followed by the segmentation, it kind of depends on your use case. So when you start off with bounding boxes, that's very good to sort of get an overall idea of how things are. But when you go for segmentation or instance segmentation, you get a tighter bounding box definitely, because you can use the instance mask and sort of go back to sort of bounding box detection as well. Generally, what I would say is instead of doing multiple annotations for the same image, try to look for that segmentation first if you really sort of are interested in the quality. And that's where your curation step comes in, right? So instead of picking a large number of images and doing bounding box, do curation, pick out the important images that are important to sort of get your performance high, do a segmentation, because you might need a segmentation later on going ahead. So you want to understand, say, depth information, right? So you want to do sort of understanding of where sort of your hand was with relation to your foot, or you want to do a understanding of where the person was with respect to a forklift, for example, that's coming in. You need to do that segmentation aspect, right? So bounding box might work for a quick and easy demo, but you might want to do segmentation first. So that's something that we often do. What we'll do is we'll do a bounding box, but we'll also do automatic segmentation, and then send curated images to a separate team that will improve those segmentations. So I would do that. I would do bounding boxes, but I'd do an automatic segmentation within that, and then send it to a separate team to do more segmentation and then improve the bounding box.
So do you always take the newest annotation as the best annotation?
Yeah, so that's a good point. So, you might have one of the ways that people do it is like they would do multiple annotations by different annotators on the same image, and then see, is that image sort of good quality? Or what they'll have is like, say, expert annotator, do a few, and then make sure that this annotator is reliable now. That often happens when you have freelancers, right? So you want to make sure the freelancer is doing it at a good quality level. So there would be some automatic checks, but then you would use some manual checks like this, right? What you'll typically do is you'll have maybe somebody who's on your workforce or on the managed team workforce who would have gold standard images, and then you would have the annotator that's to be questioned or is not reliable anymore as a new annotator to sort of run annotation or do annotation on those images and then see his quality. And that would be completely random as well. You won't tell him which images you're checking on, right? So you won't take the last one. You might want to do multiple annotations as well on certain images and take sort of the average. That's another way of doing it. But typically, we haven't used that. Typically, what we feel is that once you do the quality checks that we talked about here, it's usually good enough. And what's really important is sort of that manual check of the batches. The batch check from our team, that's the most reliable indicator. Because what happens is that the instructions that need to be sometimes repeated, that happens as well. So when you do it with the managed service, what happens is they often rotate out their teams, and those won't be caught very easily. Because maybe the new gold standard guy in that team also understands the instructions in the same way as the rest of the members. So that manual check is the gold standard right now. The way that you mentioned can be used, but it's not the gold standard.
Thank you.
Thanks.
You briefly touched on this, but something we run across a lot, I'm curious to hear insights on. When you have parameters of your system that change over time, so you might have something like the auto exposure algorithm for the camera got updated, or more majorly, the lens got switched out for the camera. Like you said, that old data is going to be valid for some applications, and purposes, but not for others. Do you have any insights on how you handle that?
Yeah, that's an excellent question. And so typically, there are a couple of ways in which we do that. One is to sort of understand domain adaptation. So domain adaptation can be when you move from one geography to the other, but it also can be when you move from one sensor to the other, right? So you would first try the domain adaptation techniques that are working. So you try more on the side of what you can do on the network side and still use the data that you have, right? Now, when it comes to using the data, typically when you train your networks, you want to use a lot of data that's from the target camera, but you also want to make sure you have a variety of other data as well. You don't want to overfit on your target camera always. So a lot of data, I said a lot of it will be thrown out, but a lot of it is still useful to you. You want to make sure that you're still using, say you had a wide angle lens, and now you have sort of a lens that is more telephoto kind, right? You will try to still use data from the wide angle one. Maybe what you'll do is you'll clip a part of the image, and then you will also zoom it. So the resolution will be slightly different, yes, but you still have data which is looking similar in some way to the telephoto lens. So there are some sort of image manipulation techniques that you can use to still work with that data. And typically what you can also do is that the data which is wide angle, you still created some interesting scenarios from that data. So you go back to your synthetic data pipeline and say, hey, these are some interesting scenarios. So synthetic data, I talked about corner cases, but sometimes you might want to recreate real world scenarios as well and give those real world camera images and then say, hey, synthetic data team, take these new camera parameters. You have already the full scene created here that you can look at. And typically these teams will also have like graphics designers and others. So they will sort of be able to create trees that look similar to your real world data and so on. So you can create those interesting scenarios and still use that old data that was there.
Do we have time?
Yeah, one more question, I think.
Okay, so first, great talk. So I just wanted to kind of share a little bit of my experience on the case in which you need to annotate data but move very fast. Mm-hmm. So you're kind of handling an annotation team as you are building these annotation instructions. And I'm going to give a very simple example. So I do consulting, and in one case we had to annotate smoke. Mm-hmm. And you can imagine that annotating smoke, like even the bounding box boundaries are very tricky. It can be confused with fog, with clouds. Mm-hmm. So even like, let's say a wildfire versus me doing something in the barbecue. So it was very, very tricky to like start the project and get going while we were like deciding on the labeling instructions. And we had this dilemma between the in-house team versus the outsourced managed team. And what happened is that we had quite some bad experiences with some companies that like kind of hide the access to the labelers behind like a project manager and therefore have slower iteration cycles. Mm-hmm. And for example, let's say that first batch takes a week. But by the way, they consistently missed the target deadlines. Yes. Mm-hmm. But they kind of, when we discovered, oh, there's this edge case on day number 2, which we have to correct right now because it impacts the quality of the batch. They had like this, oh, no, but we need to finish the entire batch before we can actually send our labelers new instructions. So if you can comment a little bit on that case.
Yeah, so this is an excellent reason why you'll have an in-house team. And sometimes for critical data, and I talked about them in sort of, will you have this or will you have that? Actually, ideally speaking, you should have both. You should have a crack team that is internal, which is going to create those. So there was another question about gold standards, right? So instead of giving the managed team the gold standard and they typically rotating their annotators around for different projects, you'll always have one consistent set of people creating those gold standards. Plus, whenever you have that critical data, you want to make sure your in-house team is doing that, right? So that's what we are actually moving towards. So initially, I had my own team. This was sort of before annotation became as a service now. I have annotation as a service. And now, then I worked a lot with sort of managed services, and I had a lot of experience, like you were mentioning. There would be, and it kind of depends on there's a human factor involved. Like how can you convince the other side? Can you get the business people involved and sort of them to talk about
Right.
this? Because as data scientists or people working on perception, we don't want to get involved in that so much.
Right. So I think that for starting, when the annotation instructions are kind of stable,
Yes.
it makes more sense to annotate closer to home.
Yes.
And then when things are much more stable or you haven't discovered any outliers,
Yes.
then maybe move to managed, which can scale better.
Exactly, yeah. So scaling is important in the managed service.
Thank you.
Yeah, thanks.
Awesome. Well, thank you again, Gaurav. That's been awesome.